All right, sorry I had to finish that video up pretty quickly. We were actually pretty much done with this problem. I was running out of time. I got 15 minutes exactly. So I just quick wrapped it up. But to wrap up one more time, what we were just finishing is our goal is to always make a straight line. We can't use a least squares regression line to make accurate predictions unless you have a straight line to work with. So yesterday we looked at what happens if it looks exponential. Well, if you take the natural log of the response variable, sometimes it makes it straight. And if that's the case, when you write the equation of the least squares regression line, you just put the natural log in front of the y. But when we tried that for this example with the fish, we tried taking the natural log of y, and it curved it kind of a different way. It didn't straighten it out as good as we would have liked. We looked at the residual plot being a curved pattern. But what I showed you is that if we take sometimes the natural log of both variables, the explanatory and the response, sometimes that's what straightens it out. You want a residual plot with random scatter. You don't want there to be any kind of pattern like this one up here. So this residual plot here shows me that nice, even, random scatter, which tells me that this is definitely linear, okay? So ultimately, this is the least squares regression line we want to use. And because we took the natural log of both, we put the natural log of the y hat as well as the natural log of the x. So flipping over to the other side, it says the line of best fit for the transformed data, because what we did is we transformed all of the data, we would say is the natural log, in this case it's the natural log of y hat is equal to this negative 4.374 plus the slope of 3.049 times the natural log of x. In fact, I'll probably even write it a little bit different. I'm going to say 3.049 times the natural log of this x. And again, just indicating which variables we took the natural log of. We took the natural log of the response as well as the natural log of the explanatory. Okay? We call this a power model. This is a power model. The exponential model is this one, where you only take the natural log of the response. A power model is when you take the natural log of the response as well as the explanatory. Now, just like with the exponential models that I showed you guys yesterday, we should be able to make predictions using the equation. So this question says, use this line to make a prediction for the weight of a rockfish that's 24 inches long. So in other words, we're going to take the 24, plug it into the explanatory, and see what it predicts for us. Okay? So I'm going to say the natural log of y hat, the prediction, is equal to this negative 4.374 plus 3.049 times the natural log of the explanatory, which we're going to plug in as 24. That's what we're going to try to predict off of. Well, you just got to type this in your calculator. There is a natural log button. You took natural log of the list. Just make sure you take the natural log of 24. So what I would have done first is calculated this. In your calculator, I would type 3.049 times the natural log of 24. In fact, I'll show you what I'm doing. 3.049 times the natural log of 24. Hit equals. Okay? So 3.049 times the natural log of 24. That's not what I have written on my paper. So I'm going to use the value that my calculator is showing here. So we're going to say the natural log of y hat equals negative 4.374 plus this 9.6899 value, okay? And then I'm just going to add that to that y-intercept. So I'm going to say, because that's a positive, or actually I know I have a negative 4.374 plus this answer that I previously had, and that's what I have for my natural log of y hat. Okay? So the natural log of y hat equals the combination of those two, which is 5.316. Now, very similar to what I did yesterday, remember the base of a natural log is an e. So you got to think about it as e to this power is equal to the y hat. So the y hat equals e to the 5.316 power. In fact, what you can do is you can go second e, and then previous answer. So it'll even take this exact version and plug it into the exponent for you. So there's your predicted amount, 203.544. Okay, so we've got our predicted amount is 203.54. And remember, we're talking about weight. And what did it say? It was weight in grams. So this is grams. So what I'm saying is if a rockfish is 24 inches long, we predict that it will weigh 203.454 grams. Now, I do want to remind you that a natural log and a logarithm, if I wrote just the word log, they're going to do the same process. You're going to have different values in here, but if you did all of the power model using logarithms instead of natural logarithms, the formula would look different and the values right here would look different, but in the end, you should get the exact same predicted amount. Okay? So, here's the next question, is what if I wanted, and it doesn't say this on here, but what if I wanted to find a residual? Well, you would need to have a value for 24, which I don't believe we had. So we're not going to actually calculate the residual, but you would do the actual minus predicted. And again, what we did here was we did the predicted. So if you had an actual, you'd go actual minus predicted to calculate the residual. So let's continue in the notes. Oftentimes, you will be asked to find the least squares regression line for weight versus length or weight against length. I just want you to be familiar with this wording. The way they word it is they usually list the response variable first. This is usually the response. This is usually the explanatory. Okay, again, response, explanatory. Because sometimes they don't come right out and say which one's the explanatory and which one's the response. So just know that when they say it like that, the second one is the explanatory, and then the first one that they list is usually the response. Okay, so it's kind of important to understand that wording. All right, so here's one other example to kind of wrap it up. And so I'm not even going to use the calculator. I kind of have things shown for you. We talked about exponential models. We talked about power models. You're going to be expected to know which one you should be using. So the following is a table that shows calculations for a 10-year term life insurance policy worth $1 million. So what I have here is the ages listed and what their monthly premium is. I mean, if we're talking about life insurance, the younger you are, the cheaper the life insurance. So this kind of makes sense. But what I have down here is 3 different graphs of the scatter plot. Notice this first one is just the predicted premium is equal to a y-intercept plus a slope times regular age. Do you see how there's no logarithms or natural logarithms attached at all? So this is a regular scatter plot. This is the actual age against the actual premium. But take a look at the graph. This is what the scatter plot looks like. They tried to fit a line to show you what a line looks like. And then below it, they show you a residual plot. As you can see, it looks like there's a curve, and in the residual plot there looks like there's a curve. So I'm not sure that this is the best model, okay? But this is just a linear model. We haven't applied any kind of logarithms to it. So this is just a plain linear model. This one, notice what they did. They took the natural log of the response as well as taking the natural log of the explanatory. Which model does both? We just talked about this one. This is a power model. Well, let's take a look at what the graph is showing us. It looks pretty linear. I mean, it's hitting the line pretty good. But remember, you don't always want to just look at the scatter plot. It's often good to look at the residual plot, because what do you notice with the residual plot? There is a curve to it. So even though the original one does look pretty straight, because the residual plot has a curve to it, I'm not sure that the power model is the best fitting model. Now what about this one? Notice this one has the natural log by the response, but there's no natural log by the explanatory, which means this is a exponential model. So that's how you tell the difference between a power model and an exponential model. Both options have a natural log of the response, but the power model also takes the natural log of the explanatory. And again, taking a look at the graph, the dots are hitting a line pretty well, but not only are they hitting the line pretty well, look at my residual plot. There's nice even scatter. There's no curved pattern at all whatsoever. So this nice even scatter tells me that this is probably the best fitting model. So the last little question here says, which model is the most appropriate for predicting monthly premium for life insurance and why? If you had to predict these, you don't want to do it off of a curved pattern of any kind. So we don't want the linear, we don't want the power. In this case, the exponential model would be the best. Okay? It is the most appropriate because it shows even scatter around the residual line Remember, this is the residual line right here, that one across the middle. And is the most linear on the scatter plot of age and the natural log of premium. Notice we only use natural log once, which is what makes it an exponential model. Okay. So I hope that was a decent wrap-up of power models versus exponential models. You probably won't have to tinker around in your calculator as much as I showed you in my calculator. I was mostly just trying to show you what happens with the graphs. But most of the questions you're going to be asked are going to be providing the graphs to you. So you won't have to be jumping back and forth between a scatter plot and a residual and knowing what's in all of your lists. Most of the time you're going to be given pictures and you're going to be asked which model is best, a linear model, a power model, or an exponential model. So know the difference between these models and know how to predict from each type of model, know how to plug in the formulas and do the wraparound method if you need to. So know how to predict for a power model, know how to predict for an exponential model, and know how to find those residuals. All right, so that wraps up the last lesson of statistics. This could very well be the last video. I hope this was helpful. From now on, you guys are going to prepare for the Chapter 12 test, and then once you're done with the Chapter 12 test, it's time to start working on your projects and to start reviewing for the AP exam. So I wish you guys the best of luck. I hope these videos were helpful. Feel free to text me anytime with questions. All right, hopefully we'll see you guys soon. Have a good day.